Hi there, we're going to look today at exercise 8D. We're going to look at what appears to be something quite similar, I suppose. We're looking at linear combinations of normal distributions, similar to stuff we've seen before, perhaps. But one way or the other, we need to have a look at this. I mean, the main thing is, I suppose, is we might have more than one normal distribution. So x might be normally distributed. Make up some numbers. 20 is the mean. Standard deviation might be, say, 4, so I'll write 4 squared. And y might be normally distributed, with a mean of, say, 25, and perhaps 3 squared as its variance. And it's what happens. What does happens if I was to add these two distributions together? Well, the good news is they are normally distributed, and the question is, what would the mean be, and what would the variance be? This is what we're looking at. And you kind of got a bit of a hint at this here, actually, on these three formulae. This is what this is all about. This is saying if I add two distributions together, the means, the mu of x plus y, is simply the mu of x plus mu of y. It's kind of what you expect. 20 plus 25 would be 45. The variance is, well, it seems on first glance that works as well. I'm saying the variance of one plus the variance of the other. 4 squared is 16, 3 squared is 9. Well, I've happened to pick nice numbers, it's actually 5 squared, 25. And it says there that works, but just be aware that it's not always right. And you might remember why, that if you have a distribution of x minus y, the normal distribution would be, well, 20 take away 25. Well, already we've got negative numbers there, but that's fine. You can have negative numbers in the distribution. But you might recall the reason why I'm still going to add those. And it's still adding them. And that's not so obvious. Let's have a look at things that we've done before. We've already shown that this is true. The expectation of one variable plus another variable. Observation, I should have said, one observation plus another observation is really just the expectation of 2 times what you expected for the distribution generally. But we also showed that that's not true for variance. The variance of one observation plus another observation is not equal to the variance of 2 times one observation. And this was the logic we've seen before. We also saw linear combinations where if you said e of ax plus by, you just bring the a's to the front, a of x plus be of y. But we saw that with variances, you have to bring it out and square, assuming that x and y are independent variables. But you know, these things will still hold for normal distributions, and this is what we saw in the past. It's because of variance of x minus y. You bring those numbers out to the front. That's 1x, I suppose, and minus 1y. But when you bring the 1 square to the front, that's fine. But when you bring the minus 1 out to the front and square, that's now plus 1, which is why we added in that slider right at the start. More generally, you need to know that if you have a linear combination of 2 normal variables, the outcome of that will also be normal. So basically I'm saying if I add a normal to a normal, it will still be normal. And that is what I want you to be aware of. 2 random variables, if they are normal, so I'm saying if x and y are both normal, then the result of some linear combination doesn't have to be just x plus y. It could be 4x minus 6y, plus even a number at the end if I wanted to make something weird up. But that resulting linear combination will still be normal. You can't have x squared in and things like that. It's only for linear combinations. So this was a slide we saw as well. If we're doing reminders, let's remind you of this. Now this says if we do a sample mean, you might remember this as a sample mean. The e of x bar is the same as e of x. This was in exercise 8b we saw this. If you don't remember it, perhaps go back and have a look at it. And the variance of an x bar, or a sample mean, is essentially the variance that you was expecting to get, but smaller, because we've done lots of sort of readings on this. Now, the first result seems obvious. This result we kind of makes sense. The average of a sample is, on average, the average of the original variable. So that is what you'd expect. This is the one which is always a bit of a surprise, and this kind of words here makes sense to me. The result demonstrates why means are so important. Their standard deviation, which can be thought of as a measure of the error caused by randomness, is smaller than the standard deviation of a single observation. The larger the sample you have, the smaller your variance of your sample will be. This proves mathematically what you probably already knew, that finding an average of several results produces a more reliable outcome than just looking at one result. That might seem obvious, it might not. Either way, learn the formula. So in this question then, this is us trying to use it. We've got, we're told what x is. It's normally distributed, 12, 15. Y is also normally distributed, and we have this linear combination. We're told that q is related to it, x plus 2y plus 3. That's fair enough. Now, if I'm going to do this, the very first thing I need to do is say that q will also be normal. That's important that we know that. Because x is normal and y is normal, this linear combination of those two things will also be normal. Notice it says x plus 2y. Now 12 plus 2y is 14, plus 3 is 17. I fully expect my mean of my new distribution q to have a mean of 17. Now what about, you've got to be a bit careful here, what about the variance of q? I've just got to do that, because 17 was easy. This, I have to say, will be the variance of x plus 2 squared times the variance of y. And adding 3 onto it won't make any difference at all. So I think this is 15. 2 squared is 4, so plus 4 times 18. Now 4 18s is 72. I reckon that is 87. So very much more spread out than the original two distributions. This is basically then a normal distribution. I'm expecting to score 17 on it, and the question says, what's the probability that I'll get over 20? I want this probability. So using my Class Whiz calculator, I'm just going to go into that menu, turn it on, always helps. Menu 8, 7, is it? What is it? It's 7, sorry, yeah. And I always want normal CD, so press 2. My lower number, it says lower, I'm going to type in 20. And my upper, now I just need to put in some huge number, so upper is, I'm going to type in 9999, that'll be big enough. 20 and 9999. My mean and my standard deviation now, and the standard deviation actually comes first, so I'm going to type in root 87. My mean, I'll type in 17. So root 87 and 17. And it tells me the probability that q is greater than 20 is 0.374, according to me at least. I've got 376. It might be I've done a much more accurate version because I had typed in root 87. Anyway, I think it's 0.374 if you do it accurately, so just see what you get. Now, this next question then, it actually is different to the last one because it doesn't give us a linear combination quite the same way. It says find the probability of x bar. Alright, so we are basically doing 4 independent observations of x and using that as a sample. So remember what we said on that first slide, that we said that e of x bar should be the same as e of x, and that's simply because if I take 4 observations, I'm expecting the first one to be 15, I'm expecting the second one to be 15. This is me trying to find e of x bar. I'm expecting a third one to be 15, I'm expecting the next one to be 15, but then of course I'm doing 4 of them, so I'm dividing by 4, so I get 60 shared by 4. It's no great surprise to learn I'm expecting the answer to be 15. So this is still 15, and that's what my slide from exercise 8b said, that e of x bar is the same as e of x. But it also said that the variance of x bar does change. It becomes the variance of x divided by n. So in this case, it's, what was it? It was 12 squared divided by 4. Now it's 144 divided by 4, which is 36. So we've got a reduced variance. And x bar then is normally distributed with mean 15 and variance 36, considerably smaller. What does that do for me? Well, I want now to find the probability. And my probability, I'm expecting to get 15. And it says, what's the probability of it being less than 14? Well, it's all this area. It's that probability there. So again, going into my calculator, I shall do it now. It's my lower value, well, that's minus 9999. My upper value, I shall say, is 14. My sigma is 6, because it's the square root of 36. And my mean is 15. And I get a probability that x bar is less than 14 of 0.434. Again, I'm hoping that's out. So yes, it is 0.434. This is an old exam question. A laminate consists of 4 layers of material C. So that's 4 layers. It's 4 different layers. So that's C1 plus C2 plus C3 plus C4, I think, and 3 layers of material D. I think this is, I'm doing this right, plus D1, D2, D3. The thickness of the layer of material has normal distribution. So it says that C is normally distributed with mean of 1 and standard deviation of 0.1. Okay, squared obviously. And D is normally distributed with mean of 8 and standard deviation 0.2. It's 0.2 squared. The layers are independent of one another. Find the mean and variance of the thickness. So I can say this is T equals. So T is going to be normally distributed. Now I've got 4 of those, so you can see that's 4 plus 3 8s are 24. So I think that is 28 comma something. Now what's my variance going to be? Well, the variance will simply be, because we've got 4 of these, but they are single observations, so I think the variance will be 4 times by the variance of the first one, the C is 0.1 squared, plus, now it's 3 observations, so 3.0.2 squared. If you do that, you get 0.16. So obviously sigma is the square root of 0.16. And all I'd say is, we don't have to square in this case, or we don't have to say 4 squared because they're single observations. Now, if we do that then we've effectively got a normal distribution. By the way, part 1 then, that is the mean, 28, and the variance is 0.16. But the total thickness exceeded by 1% of the laminate, that's what I was looking at then, jumping ahead of myself really. In the middle I'm expecting to get 28. Now there is some value, and the what thickness is exceeded by 1%. So I think 1% is here. That's meant to represent 1%. By definition then, there's a number below which 99% of them fall. I'll call that T. And to find T, we use the inverse norm of the normal distribution. So I'm just going to find this. It won't give me necessarily that straight away. You might recall we do T minus mu over sigma, and that will give me this inverse norm value. So I should perhaps have written that. So this inverse norm of 0.99 anyway, let's do that. Inverse norm of 0.99, the 0.16 square rooted for this sigma, my 28, that's right, and this gives me 28.93 for my T. Let's see what 28.9, yes. Now this is, if you like, the posh way of doing it. It works this out. But the great thing about the calculator is it tells you what it is straight off. So I can just effectively ignore that. I can write T equals 28.93. That's what my calculator has given me for that value. And it's jumped straight to it. 28.9. Interestingly there, they gave a mark for this 2.326 figure. And I wonder what they'll do on the new scheme. That's something that's worth checking. Now look, we're not going to finish all of this. There's an extra question for us to do. We'll do this in class, and when we've done that in class, we'll look at exercise 8D. Thank you very much.